Okay, so all of our representations for a dozen donuts have 17 characters. They have 12 ones for where we're putting the donuts, and they have 5 zeros to divide the kinds of donuts. So you could imagine that you could even make your donut boxes so they had slidable like paper dividers in them, right? And you could just slide them and then not have your donuts touching each other. That would be awesome. In those long donut containers where they're vertical, the donuts are vertical. I know that would mess up your sprinkle donuts. It's all right. But you also do this like when you have like a drawer of pencils, right? You can put some, or your silverware, you put some dividers in it, but maybe they can move according to how much stuff you have in each bin. But the dividers tell you when there's the difference between two different kinds of things. And then all the things go in the bins because I can't tell those things apart, right? All the donuts should be the same, of the same kind, right? All of the chocolate should be the same. All the plains should be the same. So I don't care which one of these ones is in here. I can't tell them apart. So the reason why we're doing food problems for this one is food is the biggest example that we have where we believe, or where it's pretty standard that we could get like a whole bunch of the same thing, like M&Ms, right? They're all the same. You know, some people eat different colors, and that's how they distinguish the M&Ms is by the colors. Some people don't care, and so then they wouldn't count, you know, that it was a different handful of M&Ms according to which colors they were. Some people don't like some colors, right? So this is our representation. So we have 17 characters. Now, remember that I told you last time when we count things, the important thing is not the answer. The important thing is making sure we formulate the problem. So this is what we have done. We have formulated with a form a way of figuring out how to take orders for donuts in a representation that's totally unique for every different way of ordering the donuts. So I might get the order in different orders, but it's going to be on the form the same way. So I could even feed this to a computer, and it could just, you know, actually spill out all of the donuts we needed into a box. Because it would always be in the same order. Always get the plain first, then get the chocolates, then get the raspberries, then get the blueberries, then get lemons, then get strawberry sprinkles. So we've actually transformed it into a problem a computer can do. And we've transformed it into a problem that's easy to do. Now that I have 17 spaces for either dividers or donuts, all I have to do is choose where the zeros go. Right? Or the ones. It doesn't matter which one I do, as long as I choose where they go. So out of those 17 things, I'm going to choose the places for the 5 dividers, or I'm going to choose the places for the 12 ones, because whichever one I choose, the other ones have to be the other bit. So if I choose where the zeros go, all the other numbers have to be ones. So I'm talking about numbering the positions, where this would be position number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So remember we talked about when we're making strings, we actually can order all the blanks and then toss them in a hat and then choose which ones we're going to put things in. That's what we're talking about transforming this problem into now. Since we know that the length is 17, we can now number all the blanks, and then we can just choose without replacement where we're going to put the zeros or where we're going to put the ones. Once we do the choices, the string is fully specified. So this is the mapping for problems that are called, what I call divider problems, and they have a complex description. But let's before we get to that, let's see what the formulas for these are. I wonder why they're the same. It's because the formula for combinations has k and n minus k on the bottom, so the formula for CNK is the same as the formula for CN, choose n minus k. So these two numbers, since one of them is k and the other one's n minus k, these two combination formulas end up to be the same, and it's because of the formula. And it also should make sense, because it doesn't matter which one I choose. If I only have 2 choices of what I'm going to put in a blank, if I decide where some of them are going to go, the other ones don't get to have a choice. Questions about this? So about how many different ways are there? 6,000. That's a lot of different ways to order a dozen donuts, right? So now you see if Dr. Barnes had a donut shop, there would be a form you had to fill out so that my tellers wouldn't have to stand there and take orders